Didn't work. When we rub glass rods with silk, the glass rods also become charged and repel each other. But a charged plastic rod attracts a charged glass rod. Furthermore, the plastic rod and the fur attract each other, and the glass rod and the silk attract each other. These experiments, and many others like them, have shown that there are exactly two kinds of electric charge. The kind on the plastic rod rubbed with fur and the kind on the glass rod rubbed with silk. Benjamin Franklin suggested calling these two kinds of charge negative and positive, respectively, and these names are still used. The plastic rod and the silk have negative charge. The glass rod and the fur have positive charge. Two positive charges or two negative charges repel each other. A positive charge and a negative charge attract each other. Caution: electric attraction and repulsion. The attraction and repulsion of two charged objects are sometimes summarized as like charges repel and opposite charges attract. But like charges does not mean that the two charges are exactly identical, only that both charges have the same algebraic sign, both positive or both negative. Opposite charges means that both objects have an electric charge, and those charges have different signs, one positive and the other negative. A laser printer, just like I guess right here, utilizes the forces between charged objects. The printer's light-sensitive imaging drum is given a positive charge. As the drum rotates, a laser beam shines on selected areas of the drum, leaving those areas with a negative charge. Positively charged particles of toner adhere only to the areas of the drum written by the laser. When a piece of paper is placed in contact with the drum, the toner particles stick to the paper and form an image. Well, now we gotta do stuff.
OPC drum, which prepares it for the art, rotates next to the OPC. Technically complex color printing is. Take a look at the electrophotographic process. The primary charge roller, or PCR, rotates next to the OPC drum and applies a negative charge to the surface of the OPC drum, which prepares it for the imaging process. The OPC drum is then exposed to a laser, which forms the image. This area is more positively charged than the areas not exposed to the laser. Toner is stirred in the hopper. The toner adder roller collects the toner, moving it to the surface of the developer roller. The doctor blade then levels it to the precise height. As toner moves from component to component, it develops a negative charge, which is attracted to the more positively charged image on the OPC drum. The toner on the OPC drum is then transferred to the paper. This process occurs within the 4 color cartridges in every laser printer. The paper with the toner then passes through the fusing assembly, where it is melted and fused to the paper. Any toner remaining on the OPC drum is cleaned and moved to the waste bin by the wiper blade. The latent image on the OPC drum surface is erased by the PCR. Excess toner not transferred to the OPC drum is scrubbed from the developer roller surface by the toner adder roller and returned to the toner hopper.
Wow. Okay. When you charge a rod by rubbing it with fur or silk, there is no visible change in the appearance of the rod. What then actually happens to the rod when you charge it? To answer this question, we must look more closely at the structure of atoms, the building blocks of ordinary matter. The structure of atoms can be described in terms of three particles: the negatively charged electron, the positively charged proton, and the uncharged neutron. The proton and the neutron are combinations of other entities called quarks, which have charges of positive plus or minus 1/3 and plus or minus 2/3 times the electron charge. Isolated quarks have not been observed, and there are theoretical reasons to believe that it is impossible in principle to observe a quark in isolation. Most of the atom's volume is occupied sparsely by electrons, tiny compared with the rest of the atom. The nucleus contains over 99.9% of the atom's mass. Charges of the electron and the proton are equal in magnitude. The charges of the electron and the proton are equal. Why doesn't it look equal? Protons and neutrons in an atom make up a small area-dense core called the nucleus with dimensions of the order 10 to the negative 15 meters. Surrounding the nucleus are the electrons extending out to distances of the order of 10 to the negative 10 meters from the nucleus. If an atom were a few kilometers across, its nucleus would be the size of a tennis ball. The negatively charged electrons are held within the atom by the attractive electric forces exerted on them by the positively charged nucleus. The protons and the neutrons are held within stable atomic nuclei by an attractive interaction called the strong nuclear force that overcomes the electric repulsion of the protons. The strong nuclear force has a short range, and its effects do not extend far beyond the nucleus. The masses of the individual particles, to the precision that they are known as of this writing, are these things: M sub E 9. What is this? The masses. Tiny masses. Tiny masses. The numbers in parentheses are the uncertainties in the last two digits. Note that the masses of the proton and neutron are nearly equal and are roughly 2,000 times the mass of the electron. Over 99.9% of the mass of any atom is concentrated in its nucleus. The negative charge of the electron has, within experimental error, exactly the same magnitude as the positive charge of the proton. Again, the negative charge of the electron has exactly the same magnitude as the positive charge of the proton. The negative charge of the electron has exactly the same magnitude as the positive charge of the proton. In a neutral atom, the number of electrons equals the number of protons in the nucleus, and the net electric charge, the algebraic sum of all the charges, is 0. Exactly. The number of protons or electrons in a neutral atom of an element is called the atomic number of the element. If one or more electrons are removed from an atom, what remains is called a positive ion. A negative ion is an atom that has gained one or more electrons. This gain or loss of electrons is called ionization. When the total number of protons in a macroscopic object equals the total number of electrons, the total charge is zero and the object as a whole is electrically neutral. To give an object an excess negative charge, we may either, not we, but some other we, may either add negative charges to a neutral object or remove positive charges from that object. To give an object an excess negative charge, we can add, well, yeah, why can't you, they could just say to make an atom negative, put more electrons because they're negative, or take them away. That's it. In most cases, negatively charged or highly mobile electrons are added or removed, and a positively charged object is the one that has lost some of its normal complement of electrons. Oh gosh. All these words for nothing. Implicit description, blah, 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 blah. Principle of conservation of charge. Conservation of charge. The algebraic sum of all electrical charges in a closed system is constant. The algebraic sum of all the electric charges in a closed system is constant because it's closed. If we rub together plastic and fur, both uncharged in the beginning, the rod acquires a negative charge. So one of them is positive and one of them is negative. And they have the same magnitude since it has lost as many electrons as the rod has gained. Oh, hence the total electric charge of the two objects together does not change. In any charging process, charge is not created or destroyed. It is merely transferred from one object to another. Oh my gosh! So the conservation of charge is like the conservation of energy. See? Conservation of charge is thought to be a universal conservation law. No experimental evidence for any violation of this principle has ever been observed. Even in high-energy interactions in which particles are created and destroyed, such as the creation of electron-positron pairs. The total charge of any closed system is exactly constant. The second important principle is the magnitude of the charge of the electron or proton is a natural unit of charge. Every observable amount of electric charge is always an integer multiple of this basic unit. Every observable amount of electric charge is always an integer multiple of this basic unit. We say that charge is quantized. A familiar example of quantization is money. When you pay cash for an item in a store, you have to do it in 1-cent increments. Cash cannot be divided into amounts smaller than a penny. And an electric charge cannot be divided into amounts smaller than the charge of one electron or proton. The quark charges, plus or minus a third and plus or minus 2/3 of the electron charge, are probably not observable as isolated charges. Thus, the charge on any macroscopic object is always zero or an integer multiple, negative or positive, of the electron charge. Understanding the electric nature of matter gives us insight into many aspects of the physical world. The chemical bonds that hold together to form molecules are due to electric interactions between the atoms. They include the strong ionic bonds that hold sodium and chlorine atoms together to make table salt, and the relatively weak bonds between the strands of DNA that record your body's genetic code. When you stand, the normal force exerted on you by the floor arises from electrical forces, electric forces between charged particles in the atoms of your shoes and the atoms on the floor. The tension force in a stretched string and the adhesive force of glue are likewise due to electric interactions of atoms. Most of the forces on this water skier are electric. Electric interactions between adjacent molecules give rise to the force of the water on the ski. The tension in the tow rope and the resistance of the air on the guy, electric interactions also hold the atoms of the body, of the guy's body together. Only one wholly non-electric force from Jesus acts on the skier, because it's one wholly non-electric force. The force of gravity, 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 gravity. Okay, now I have to test my understanding. There are two charged objects that are repelling each other through some mysterious electric force. These charges on the objects are I, one positive and one negative, 2, both positive, 3, both negative, 4, either, or any of, either 2 or 3, or any of them. Whatever. Okay, so the charges on the objects. So one is going to be positive and one is going to be negative. So the answer is one positive and one negative. I got it wrong. I just read this whole chapter for nothing. Two charged objects repel if their charges are of the same sign, either both positive or both negative. I'm not even on drugs, Joshua. I'm not even on drugs. I have no understanding. I've tested it and I have none. I've put it to the test. Okay, continue. Moving on. Oh wait, do I have to move on? We'll do it. We'll just do it. Some materials permit electric charge to move easily from one region of the material to another, while others do not. This picture here shows a copper wire supported by nylon thread. Suppose you touch one end of the wire to a charged plastic rod and attach the other end to a metal ball that is initially uncharged. You then remove the charged rod and the wire. When you bring another charged object up close, really close to the ball is attracted or repelled, showing that the ball has become electrically charged. Electric charge has been transferred through the copper wire between the ball and the surface of the plastic rod. There's a ball, there's a wire, and there's some string, and there's a plastic stick. Let's just call it a plastic stick. There's a plastic stick on a metal ball. It's copper. It's some string. So, the negatively charged plastic rod is repelling the ball. So that must mean that both the ball and the stick are negative, like the picture shows. What happened? Copper is a good conductor of electricity. Why? We don't know. But nylon is a good insulator. The copper wire conducts charge between the metal ball and the charged plastic rod to charge the ball negatively. Afterward, the metal ball is repelled by the negatively charged plastic stick and attracted to a positively charged glass stick. sticks, but they're made of glass. The copper wire is called a conductor of electricity. Reason not specified. If you repeat the experiment using a rubber band or a nylon thread in place of the wire, you find that no charge is transferred to the ball. These materials are called insulators. Conductors permit these easy movements of charges through them, while insulators, they do not. The supporting nylon threads are insulators, which prevent charge from leaving the metal ball and the copper wire. As an example, carpet fibers on a dry day are good insulators. As you walk across a carpet, the rubbing of your shoes against the fibers causes charge to build up on you, and this charge remains on you because it cannot flow through the insulating fibers. If you then touch a conducting object such as a doorknob, a rapid charge of transfer takes place between your finger and the doorknob, and then you get shocked, and then you say, ow, or you don't. One way to prevent this is to wind some of the carpet fibers around conducting cores, whatever the fuck that is, so that any charge that builds up on you can be transferred harmlessly to the carpet. Another solution is to coat the carpet fibers with an anti-static layer that does not easily transfer electrons. So we have this mysterious, unidentified anti-static layer to your shoes, and it prevents charge from building up on you as a person in the first place. Metals are good conductors. Non-metals are insulators. Within a solid metal, like copper, one or more outer electrons in each copper atom become detached so that they move freely throughout the material, just as the molecules of a gas can move through the spaces between the grains within a bucket of sand. The other electrons remain bound to the positively charged nuclei, which themselves are bound in nearly fixed positions within the material. In an insulator, there are no or very few free electrons, and electric charge cannot move freely through the material. So we'll call them slave electrons. Or maybe we won't. Yeah, we will. They are slaves because they are not free. Like everybody addicted to technology. They're slaves. They're slaves. Some materials called semiconductors are intermediate in their properties between good conductors and good insulators. We can charge a metal ball by using a copper wire and an electrically charged plastic rod. This process, some electrons that are extra on the rod are transferred from the rod to the ball, leaving the rod with a slightly negative charge. But there is also another technique that is different, where the plastic rod can give another object, any other object, a charge of the opposite sign without losing any of its original charge. This process is called charging by induction. If you look at this picture right here that has a charge, that is an example. An uncharged metal ball is supported on an insulating stand. When you bring a negatively charged rod near the ball without actually touching the ball, the free electrons in the ball are repelled by the excess electrons on the rod, and they shift toward the right, away from the rod. They cannot escape from the ball because the supporting stand and the surrounding air is insulating it. So we get extra negative charge on the right surface of the ball and a deficiency of negative charge, which is basically another way of saying a net positive charge on the left side of the table. These excess charges are called induced charges. So, induced charges are charges on arbitrarily identified directions, arbitrarily designated directions. A negative charge, a positive charge, rods removed, electrons rearranged, ball has electron deficiency. Not all of the free electrons move to the right surface of the ball. As soon as any induced charge develops, it exerts forces towards the left on the other free electrons. Is it possibly because to balance it? These electrons are repelled by the negative induced charge on the right and attracted towards the positive induced charge on the left. The system reaches an equilibrium state in which the force toward the right on an electron due to the charged rod is just balanced by the force towards the left due to the induced charge. If we remove the charged rod, the free electrons shift back to the left and the original neutral condition is restored. What happens if, while the plastic rod is nearby, you touch one end of a conducting wire to the right surface of the ball and the other end to the earth? The earth is a conductor, and it's so big that it's practically an infinite source of extra electrons. Some of the negative charge blows through the wires to the earth. Now suppose you disconnect the wire and then remove the rod. A net positive charge is left on the ball. The charge on the negatively charged rod has not changed. The earth acquires a negative charge that is equal in magnitude to the induced positive charge remaining on the ball. Example demo here.
So here I have a metal can, aluminum can, which can freely roll along the table. In my hand I have a PVC rod, which I can charge negatively with this piece of felt cloth. Now, if I charge the rod and bring it near the can, what will happen? Will the can roll towards the rod? Will it move away from the rod, or will it stay put?
Away. It goes towards.
So as you can see, the can rolled towards the rod. This is because the can is neutral. When I bring up the negatively charged rod, it induces positive charge on the side of the can facing the negative rod. Positive charge is attracted to the negative charge in the rod. Now, we can repeat the experiment, but this time we have an acrylic rod. When rubbed with this paper, will produce a positive charge. What will the can do now? Will it move towards the rod? Will it roll away from the rod, or will it stay put? So, once again, the can rolls towards the rod. And once again, this is because the positive charge on the rod induces a negative charge on the side of the can facing the rod, and the positive and negative charges attract.
So enthusiastic. Finally, we note that a charged object can exert forces even on objects that are not charged themselves. If you rub a balloon on the rug and then hold the balloon against the ceiling, it sticks, even though the ceiling has no net electric charge. After you electrify a comb by running it through your hair, you can pick up uncharged bits of paper or plastic with it. How is this possible? The comb that is negatively charged is an insulator. Positively charged comb is also an insulator. As a result, a comb with either sign of a charge attracts a neutral insulator. By Newton's third law, the neutral insulator exerts an equal magnitude attractive force on the comb. This interaction is an induced charge effect. Even in an insulator, electric charges can shift back and forth a little when there is charge nearby. This negatively charged plastic comb causes a slight shifting of charge within the molecules of the neutral insulator, an effect called polarization. The positive and negative charges in the material are present in equal amounts, but the positive charges are closer to the plastic comb and so feel an attraction that is stronger than the repulsion felt by the negative charges, giving a net attraction force. The electric forces depend on distance. That's in 21.3. Note that a neutral insulator is also attracted to a positively charged comb. Now the charges in the insulator shift in the opposite direction. The negative charges in the insulator are closer to the comb, and they feel an attractive force that is stronger than the repulsion felt by the positive charges in the insulator. Hence, a charged object of either sign exerts an attractive force on an uncharged insulator. I'm going to repeat that. A charged object of any sign produces an attractive force on an uncharged insulating thing. Could be anything. Maybe. Spray negatively charged paint droplets on a metal door to paint it, and the positive charge will be induced on the door. An electrostatic painting process. A metal object is to be painted, and the metal object is connected to the earth or ground, and the paint droplets are given an electric charge as they exit the spray nozzle. The induced charges of the opposite sign appear in the object as the droplets approach. They attract the droplets to the surface. This process minimizes overspray from clouds of stray paint particles and gives a smooth finish. So you have to know physics to paint. Otherwise, you cannot paint. And if you have been painting this whole time, you go to jail. You have two lightweight metal spheres, each hanging from an insulating nylon thread. Got two balls on a string. They each got their own string. One of the balls is negative. The other one is nothing. If they are both close together but not touching, will they attract each other? Repel each other? No force. One of them is negative, the other is no charge. They will repel. They will not repel. They will not attract. Nothing happens. Nothing happens. Well, if something has a negative charge and something is neutral, that means the object with a satisfactory amount of electrons is cool, and the other one is it's negatively charged. That means it's lacking in electrons. No, it's negatively charged, so it has more electrons than it wants to have. So we have a ball that has more electrons than it wants, and there's something else that's cool. So the one that's cool doesn't want any more electrons because it's fine the way it is. So it's gonna be repelled, because it's gonna be like, get away from me. I don't want your extra electrons. I'm fine. You now allow the two balls to touch. Once they've touched, will the balls attract, repel, or no force? No force. I don't understand. I don't even understand the answer. Oh. I and I.